In this video, we're going to look at arithmetic operations on matrices. So we're going to look at ideas like how to add matrices together, how to multiply matrices, and these tools will help us as we continue to solve systems of equations throughout Chapter 6. So first, let's define the size of a matrix. Size is the number of rows times the number of columns. And we always say it in that order. So you talk about number of rows first, then number of columns. So for example, if you look at this matrix A that we've got in front of us, we would say, well, it's got 3 rows. Here are the different rows. And it's got 2 columns. So we would say A is 3 by 2. Now let's look at what it means for 2 matrices to be equal. So if 2 matrices are equal, it means corresponding entries in the 2 matrices are equal. So let's figure this out through an example. Let's say we're told these 2 matrices are equal and we want to use that information to find x and y. Well, let's look at the top left entries. They have to be the same in both matrices. That works out. Let's look at the top right. So 2x would have to equal 8, and that's giving us information about x. So we could say 2x equal 8, in other words, x equal 4. And we found the value of x. Continuing our way through the matrix, we're just going to keep saying that corresponding entries are equal. So in the bottom left, we have y plus 1, and that has to equal 7. So we can set up an equation here, y plus 1 equals 7. That means y equals 6. And then continuing to our last entry in the matrix, the bottom right entries have to be equal as well, and they are. So 9 equals 9. So we've succeeded in finding the values of x and y, but more importantly, we learned what it means for 2 matrices to be equal, which is that corresponding entries have to be equal. Now let's define 2 special types of matrices that will come up quite often in Chapter 6. A square matrix has the same number of rows as columns. So it could be a 2 by 2 matrix, a 3 by 3 matrix, a 4 by 4 matrix, etc. The identity matrix is a special type of square matrix. So it's got 1s along the main diagonal from the top left to the bottom right, and it's got 0s everywhere else. So what we have here is the 2 by 2 version of the identity matrix. And for short, we're going to call the identity matrix I. So if we're talking about a 2 by 2 matrix, I is this highlighted matrix here. If we were looking at a context of 3 by 3 matrices, we've got a 3 by 3 version of the identity matrix. We would still call it I. It would still have 1s along this main diagonal from the top left to the bottom right, and it would have 0s everywhere else. So we figure out the size just from the context. So now let's try some operations on matrices. We're going to try doing 3 times A. So what that means is multiply every entry in your matrix by 3. So looking up at the matrix A and just multiplying by 3, you'd have 3, 9, -6, and 12. We can do things like A plus B. And what that means is to add up the corresponding entries of A and B. So if we look at the top left, we'd go 1 plus 6 is 7. Top right, 3 plus 7 is 10. For the bottom left, -2 plus 8 is 6. And then for the bottom right, 4 plus 9 is 13. So we're just performing the addition operation, but just doing that on corresponding entries. You can do something a little bit more complicated like 2a minus 5b. And in order to do that, I would think about first calculating 2a. And separately, I would think about calculating -5b. So we could do the multiplication first, and then we could add those matrices together. So let's figure out what 2a looks like. Just double all of the entries in A. You'd have 2, 6, -4, 8. And we're going to add on -5b. So taking everything in B, multiplying by -5, you'd have -30, -35, -40, and -45. So now we're going to do the addition operation. So in the top left, 2 plus -30 is -28. Then we'd have 6 minus 35 is -29. -4 plus -40, -44, and then 8 minus 45 is -37. So there we have our matrix. Now, quick examples. Say we try to add together two matrices that have different sizes. So for example, we've got this 2 by 1 matrix and we're trying to add it to a 1 by 2 matrix. Something like this is undefined, meaning it's not possible to complete that operation. So anytime the sizes are different, your addition will be undefined. Now we want to move towards multiplying matrices together, and before we can do that, we need to look at a new type of operation called the dot product. So this gives us a way of multiplying a row with a column, and the symbol that we use for this operation is just a dot. Okay, so we're going to see how to take the dot product of the row 1, 3 with the column 1, 5. Well, the way the dot product works is you multiply the first numbers together, so 1 times 1, and you multiply the second pair of numbers together, so 3 times 5, and you're just adding the results. So you're doing a product plus another product, and that's just going to boil down to a number. So we'd have 1 plus 15 is equal to 16. Okay, we could get even better practice if we took a row that was a little bit bigger. So we could do the row 1, 4, 1, and now we'd be dotting it with a column that has 3 numbers in it, let's say -1, 6, 2. And so the way the dot product works, you multiply the first pair of numbers together, 1 times -1. You add on the product of the second pair. So we're adding on 4 times 6, and then we're adding on the product of the last numbers, so 1 times 2. So you're just forming these little products and then summing them up. So in this case, we'd have -1 plus 24 plus 2. And you can do this on your calculator, might make it a little bit easier. So that gives us 25. So with the dot product in mind, now we can talk about how to multiply matrices. So let's say we want to multiply matrix A and matrix B together. So let's define how we calculate A times B. Well, matrix multiplication involves a whole bunch of dot products. So to help us visualize the dot products, we're going to circle the rows of the first matrix, and we're going to circle the columns of the second matrix. So it's always rows of the first matrix, columns of the second matrix, and we're going to form some dot products. So specifically in the row 1, column 1 entry, we're going to have row 1 dot product with column 1. This entry here is row 1 and column 2. So we're going to go row 1 dot product with column 2. We'll see that AB actually has 3 rows and 2 columns. So we'll talk more about that later, how we actually know the size of AB. But as we go through this matrix, we're just always doing the dot product of the appropriate row and column. So for example, in this position here, we would just say, okay, that's in row 3 and column 2. So that means we would be doing the dot product of row 3 with column 2. And so if we filled in all the details, this would look like row 2 dot column 1, row 2 dot column 2, row 3 dot column 1. So you circle rows of the first matrix, columns of the second matrix, and in each position, you're just taking the dot product of the appropriate row and column. All right, so let's try some calculations. We'll get a bit more practice with our dot products. So what we're going to do here is calculate the 6 different numbers. So when we look at this top left entry here, that's row 1, column 1. So we're taking row 1 of A, and we're doing the dot product with column 1 of B. Okay, so let's figure out our dot product. Our products would be 4 times 1 plus 6 times 1 plus 1 times 2. So that would give us 12. So since we're still getting the hang of the dot product, I think I'll write a few of these out the long way so that we can see where the calculation's coming from. So this position here is row 1, column 2. So we're going to take row 1 of A and dot it with column 2 of B, and let's think about our dot product. Our products would be 0, 6, and 3, and if we add those up, that's 9. So let's just continue that way through our matrix. So for this position here, that's row 2, column 1. we'd be going 0, 2, 3, dotted with 1, 1, 2. So our products are going to be 0, 2, and 6, which is 8. So for this position here, row 2, column 2, so it's 0, 2, 3, dotted with 0, 1, 3. Our products are 0, 2, and 9. So if we add those up, that's going to be 11. And then let's see if we can work out the bottom row without writing anything down. So typically we don't do any side work when we're doing this matrix multiplication. Okay, so for the bottom left, we're doing 1, 1, 1, dotted with 1, 1, 2. The products would be 1 plus 1 plus 2, that would be 4. And then for this position here, bottom right, we're going 1, 1, 1, dotted with 0, 1, 3. So our products would be 0, 1, and 3, and that would give us 4. So there we have our product AB. So now let's talk about the size of AB, because often it's helpful to be able to predict in advance how big your product is going to be. So the size of AB that we just calculated is, well, we always talk about number of rows times number of columns. So it's 3 by 2. Okay, and let's see if we could have figured that out just from looking at the original matrices A and B. So what we did is we multiplied A and B together. A was a 3 by 3 matrix, and B was a 3 by 2 matrix. So when you multiply matrices together, these inner numbers must be equal. And the reason for that is just to make sure that your dot product can be completed, to make sure that dot product is defined. So I'll just draw a picture over on the side here. So A is 3 by 3, B is 3 by 2. So what you're doing is you're taking rows of the first matrix and columns of the second matrix. So to say these middle numbers are equal is to say there's the same number of entries here as there is here. If you had a different number of entries, then you wouldn't be able to compute that dot product. Okay, so those inner numbers must be equal, and then the outer numbers give the size of AB. So the outer numbers help you predict how big your matrix AB is going to be. So what's interesting here is that the matrix BA is undefined, and we can use size to figure out why, because B is a 3 by 2 matrix, A is a 3 by 3 matrix, and we said the inner numbers must be equal. In order for matrix multiplication to make sense, those inner numbers must be equal, and we see that that's not the case here. So that means we can't calculate B times A. Okay, let's draw a picture to understand why. So B is 3 by 2, A is 3 by 3. And remember, what we're supposed to do is circle rows of the first matrix, columns of the second matrix. So, we have a problem. We're not going to be able to compute the dot product when there are 2 entries over here, but 3 entries over here. That dot product just isn't defined. So as soon as you see something like that, you go, okay, so I can't do that multiplication. So what we have on the right is a visual explanation of why BA is undefined. And what we have on the left is an algebra explanation of that exact same idea. So when you see the inner numbers not being equal, you can't do your matrix multiplication. So I think just to make this crystal clear, I'll say if you take something like this and you try to do a dot product with something like that, that is undefined because you have different numbers of entries in the row and the column. So we figured out something sort of interesting here, and that is that AB is definitely not equal to BA. So we calculated AB and we found it to be this matrix here. And then we thought about BA and we figured out that it's not defined. So AB and BA are very different. So let's write this up as a fact. AB in general is not going to equal BA. And what that means is order matters when we multiply matrices. So it matters which one is on the left and which one is on the right. So let's do a bit more practice with matrix multiplication. We've got 2 matrices, C and D, and we're going to try to calculate CD and also DC. Well, what I recommend with matrix multiplication is that we think about size first. So when we think about CD, size of C is 2 by 4. and size of D is 2 by 2. And we said that these inner numbers must be equal in order for matrix multiplication to be defined. So that tells us that CD is undefined. If you want a visual way of thinking about this, we'll draw a picture on the side. So here's C, here's D. We're supposed to be taking rows of our first matrix and doing a dot product with columns of our second matrix. And you can see that there's different numbers of entries in that row and column. So you're just not going to be able to build that dot product. So to draw this picture is the same thing as to say these middle numbers must be equal, and they're not. So CD is undefined, and that's all we need to say there. Okay, so let's call that part A. Part B, we're going to do the calculation the other way around, DC. Well, D is 2 by 2. C is 2 by 4. The inner numbers are equal. That's good. That tells us that we're going to be able to do our multiplication. And the outer numbers are going to predict the size of DC. And it's really helpful to know that in advance, because now I can say, okay, DC equals, and I know what the shape of DC is going to be now. It's going to be a 2 by 4 matrix. So let's go ahead and figure out the numbers that go in here. So I think what I'm going to do is just copy D and C side by side so that we can see them. And then we know the result is going to be 2 by 4. Okay, so D is 1, 0, 3, negative 1. And we'll fill in C as well, 1, 2, 3, 6, and 1, 1, 0, 1. So most important thing is to circle the rows of the first matrix and columns of the second matrix. And then we're going to form our dot products. So we're going to do the first row dotted with the first column. Dot product is 1 plus 0 is 1. And then we're going to stick with that first row, but we're just going to move across the different columns. So now we're doing this dot product, 2 plus 0 is 2. And keep moving across those different columns, and that's just building up the first row of your product. So now this dot product, 3 plus 0 is 3. And then finally, this dot product, 6 plus 0 is 6. So that's our first row done. So now we're going to move into working with the second row with the various columns. So our first dot product is 3 minus 1 is 2. Second row, second column, 6 minus 1 is 5. 9 plus 0 is 9. And then finally, 18 minus 1 is 17. And there we have our product DC. So let's talk a quick fact about the identity matrix. So let I be the identity matrix. Let me just remind us on the side what the identity matrix looks like. So if we're talking about a 2 by 2 matrix, it looks like this. If we're talking about a 3 by 3 matrix, it'll look like that. So it's got ones from the top left to the bottom right, and it's got zeros everywhere else. And the shorthand notation for that identity matrix is just I. Okay, so let's let I be the identity matrix. Useful fact that we're going to be using throughout this chapter is that if you take any matrix A and you multiply it by I, you get back your original matrix A. And this is also true if you do it in the other order. So I times A equals your original matrix A. It's true for any matrix A. So let's just confirm that with an example. So let's say A is the matrix 1, 2, 3, 4, 5, 6. And we are going to confirm that AI equals A and also that IA equals A. So two reasons for doing this. One is that these formulas will be useful later in the chapter. Second reason for doing this is just it helps us practice matrix multiplication. So part A, let's start with A times I. So we're going to go 1, 2, 3, 4, 5, 6. And here we need a matrix with 3 rows so that we can actually form the dot product of that row with that column. And so that tells us, okay, it's going to be the 3 by 3 version of the identity matrix, just from thinking about what sizes are going to be compatible. So thinking about the size, A is 2 by 3, I is 3 by 3. So we're going to end up with a 2 by 3 matrix. And let's just calculate our dot products. So doing this row with this column, our dot product is 1. And as we move across the various columns, we're going to get a dot product of 2 and then a dot product of 3. Okay, so now let's move into the bottom row. This row, we're going to imagine doing the dot product with the various columns. So dot product with that column gives us 4. Dot product with second column here gives us 5. And then dot product with the third column gives us 6. So yeah, sure enough, we do end back at our original matrix A. So let's just confirm quickly that if we did this in the other order, it would also work. So we want to try I times A and confirm that that comes out to A. So we're going to have some matrix here, and then we're going to have our matrix A sitting over here. And let's think about what the size of the identity matrix should be. So remember, you're circling rows of your first matrix, columns of your second matrix. And if we want to have the same number of entries circled, then now we're going to need a little 2 by 2 identity matrix to make the sizes compatible. Take the first row with the first column. Our dot product is going to be 1. And as we stick with that first row, but we think about dot products with the various columns, we're going to have a dot product of 2 and then a dot product of 3 as we work across that top row. Okay, and then work with the second row. Second row, first column, dot product is 4. Second row, second column, dot product is 5. And then second row, third column, dot product is 6. And yep, sure enough, we end back with our original matrix A. So A times I will always equal A, and I times A will always equal A. So matrix multiplication is pretty weird. It feels very strange the first time you see it, but there's a very good reason why it works the way it does. So let's explore that a little bit through an example. Let's just ask, why do we multiply matrices like this? Well, let's take 3 matrices here. So A just has some numbers in it, X has some variables in it, and B has some numbers in it. And the question is just asking us to expand the following equation, AX equal B. Okay, so what we're going to do here is just fill in our matrices. Here's A. That's going to get multiplied with X, and we're going to say that's equal to B. So when we say expand this, this just means do matrix multiplication on the left side. So let's try it. We're going to circle rows of our first matrix, circle any columns of our second matrix. So in this case, there's just one column. We're taking a 2 by 2 and multiplying it by a 2 by 1. So we're going to end up with a 2 by 1 matrix that looks like this. Okay, so let's try our dot product. We're supposed to go 1 times X plus -4 times Y. Okay, so we would just call that 1X minus 4Y. Often we don't write the leading one, so just X minus 4Y is a better way to say that. And for our bottom row, if we take the dot product of this guy with that guy, 2 times X plus the second product, which is 3 times Y. Okay, so that's what we get from doing the matrix multiplication on the left, and we're saying that's equal to 7, 6. Okay, now think back to when we talked about what it means for 2 matrices to be equal, right at the beginning of this video. It means that corresponding entries are equal. So you're really getting 2 pieces of information for the price of 1. One piece of information says X minus 4Y is equal to 7. That's just from looking at the top entries and saying those are equal. And we get another piece of information from looking at the bottom entries. 2X plus 3Y equals 6. So actually what we've produced here is a system of equations. So the reason that matrix multiplication works the way it does is so that we can use it to study systems of equations. Solving systems of equations is our big goal in Chapter 6. It's the thing we really care about, and matrix multiplication is just a tool to help us do that. So what we've learned over the course of this example is that when you take an equation that looks like ax equal b, that's really representing a system of equations. So a just has some numbers in it, x has some variables in it, and we're saying that's equal to some other numbers. That's just a way of encoding a system of equations. It's a fast way of writing down a system of equations. So let's make a definition here that's going to be useful. When we see the equation ax equal b, we'll say that's called a matrix equation. So matrix equation means the formula ax equal b. So our goal here is to write the system of equations as a matrix equation. So we have to remember what this term matrix equation means. It means the formula ax equal b. And let's figure out all the details here. So a is going to represent the coefficients of your system of equations. X is going to represent your variables. And the variables are always going to be written in the form of a column. And the reason we have to insist on that is just so that when you actually do the multiplication of this row with that column, that the sizes are compatible. Okay, and then we're going to say this is equal to, and over on the right side, we're going to have the constants from the right side of the system. And again, we have to insist that that's written as a column, just so that the size of what we have on the left side is the same as what we have on the right side. Okay, so let's look up at our system of equations here and just pull out our constants, or sorry, our coefficients. Let's do those first. So pulling out the coefficients in the order in which they appear, 2, -9, 7, and 3. So that's our matrix A representing the coefficients. Matrix X represents the variables, just in the same order that they appear in the system of equations. So that's X and Y. And then when we say constants, we mean the numbers from the right side of the system. So the 12 and the -16. So last problem for this section, we're going to do an applied version of a matrix multiplication. So let's imagine that an investment firm has 3 clients, and we'll just call them client X, Y, and Z. So these clients have different amounts of assets. So let's say all these assets are measured in millions of dollars. Okay, now we're representing this in a matrix because each of these 3 clients has 3 different types of assets. They have bonds, they have equities, and they have real estate. So we've got this matrix just encoding how many assets in bonds, how many assets in equities, how many assets in real estate for each of these 3 clients. Okay, now let's say we're looking at some historical data and we know last year's return in percentage for each of these 3 asset classes. So let's say bonds returned 2%. Well, we're going to write that as a decimal. So we're going to write 0.02 instead of 2%. Equities 0.1, so that means a 10% return on equities for last year. And real estate 0.25, meaning a 25% return on real estate last year. So our goal is to calculate the total earnings in millions of dollars for each client last year. Well, first observation is that there must be a multiplication involved. So let's write down our 2 matrices side by side here. So we've got our different clients here, X, Y, Z. We've got our different asset classes, so bonds, equities, and real estate. And then we've got a second matrix that tells us the return for those 3 asset classes, so the bonds, equities, and real estate. Okay, so here are our returns, 0.02, 0.1, 0.25, and then we'll fill in the numbers for the assets as well. So client X has 10 million in bonds, 40 million in equities, and 50 million in real estate. For client Y, it's 30, 30, 40. And for client Z, 90, 5, 5. So it turns out that each of these clients has $100 million in assets. They're just spread differently across the different asset classes. Okay, so what we're going to do here is do a matrix multiplication. I'm going to circle the rows of the first matrix and columns of the second matrix. And if we think about sizes, we're taking a 3 by 3 times a 3 by 1. So at the end of the day, what we're going to have is a 3 by 1. Now what's interesting here is the categories. So in order for this matrix multiplication to be meaningful, we have to have set it up so that B is going to multiply with B, E is going to multiply with E, R is going to multiply with R. In other words, you should be taking your assets in bonds and multiplying them by the return on bonds. So it's important that those categories match up. And of course, it's important that the sizes of the matrix should be compatible. So let's write down these two guidelines. So sizes must be compatible. We know that from our previous discussion. But because this is an applied problem, the categories must match up. And that means when you do your dot product, B should be landing on top of B, E should be landing on top of E, or E should be multiplying with E if you want to say it that way. Okay, so effectively by doing the dot product then, the bond category cancels out, the equity cancels out, the real estate cancels out, and all we're left with is these categories X, Y, Z, telling us in millions of dollars what these different clients' returns were. So we're calculating returns in millions of dollars. Okay, so let's try our first dot product. First row, dotted with that column, we'd go 10 times 0.02 plus 40 times 0.1 plus 50 times 0.25. Feel free to grab the calculator for this. That comes out to 16.7. So client X earned a return of $16.7 million last year. This should say millions of dollars. Okay, so let's try the dot products and get our returns for clients Y and Z. So for client Y, we're doing this dot product, the second row with the column there. I'll just do some scribbling up at the top of the screen. So we're going to go 30 times 0.02 plus 30 times 0.1 plus 40 times 0.25. Okay, so if we pull out our calculator there, that's going to be 13.6. And then finally to do client Z, we're doing bottom row with that column. So it's going to be 90 times 0.02 plus 5 times 0.1 plus 5 times 0.25. And again, we can use our calculator there. So 3.55. So it looks like client X was the winner. He made the biggest return in millions of dollars. So that's our video on arithmetic operations on matrices. Thanks for watching.